Okay, let's talk about TensorFlow. What are tensors and how do we use them to do some mathematics? Now, there's some pretty serious motivation for this because along the way of dealing with images and things like that, we're going to have to do some mathematics, and an image is basically a two-dimensional matrix of numbers. So understanding something about the capabilities of using TensorFlow as just a math tool is pretty important to what we're trying to do. Now, the first question is, what is a tensor? Because that's probably not a term you've run into before. But a tensor, in a general sense, is some sort of a n-dimensional grid of numbers. And the simplest tensor is a grid that just has one number in it, and that's going to be our first example. And that's the one that you've seen lots of times with numbers. In this case, we're going to take a times x, which is minus 5, or 5 times minus 2, and then we're going to add b, which is, ax plus b. You've probably seen that in some algebra class before, as the point value solution for a linear line, and we'll get the result. And let me actually run that once, but here's the piece of code for it. And this piece of code, tf1.py, it'll take a second because what it's actually doing here on this system is it's actually turning this set of code into a program that it's running on a graphics processing unit. And that's kind of a slow process. You'd go, why would you want to do that? Because the CPU in my laptop is probably more than most people have in their laptop. I have a 8-core Intel i9 processor, which is about the top that you can get in a laptop. So it has 8 cores or 16 potential threads that it can run concurrently. The processor that I have attached to the system is an external graphics processing unit with 4096 cores. And for anything of any significant size, the 4096 is way faster than the 8. So even if those cores are not quite as fast, it's still a way faster solution for anything of any size. Now, taking a simple thing like this and, multiplying and adding some floating point numbers could be done in Python a lot faster. But the point is that we end up with a result of 3, which is actually the correct result. But that is done using a system that can scale to much larger things. Now, this is the 1-ish number. And I mentioned that this is n-dimensional. One of the powers of machine learning is to do stuff in way larger dimensions than us human beings can deal with. And we're going to look at some vectors, some 2-dimensional. We're going to look at some 3s. But the big picture is, what if I'm doing real estate and I want to forecast the price of a house? Not the price that it will sell at, the price that it should sell at. And there's a difference between those two. So let's say I have, 8,000 different possible variables that I'm going to use in this. And some of these variables are things like the address or the location or the neighborhood type or how much other houses in the neighborhood have sold for. And so my n-dimensional grid, isn't a 1 or a 2 dimension, it's an 8,000 dimension grid. So this is part of the capabilities. I asked you to read the article about GPT-3 where it had gone off and written an article that we shouldn't be afraid of artificial intelligence. This is the one in The Guardian. Short, interesting read. I will point out that the dimensions that GPT-3 is using in terms of building its operations, and it isn't built on TensorFlow, but it is got the same properties, is 1.3 billion dimensions. That's a bunch. 1.3 billion dimensions. So when we talk about these tensors as being multidimensional grids, yeah, but this also means that we could have a lot of dimensions. So let's look at a little bit more complex example than TF1, where we just do a point slope form. And let's do some addition of some vectors and let's solve a matrix. Some of you have probably not seen matrices. So let's start with the addition of just two matrices. So let's just take a 3x3, a rank 2 tensor, so it's two-dimensional, and let's use TensorFlow to just add some matrices values together. So the first one, okay, is this 3x3 matrix that I'm going to call matrix A. That's the name of it in TensorFlow. And I'm just going to set it to all ones. And then I'm going to create a constant matrix. And that's over here with these constant values. So it's got 1, 2, 3 vectors of 3 values each. And we'll call that matrix B. And when I run this, it'll print out the first two matrices, the values that we have here, which they're just values. And then we'll take this and we'll construct a program in TensorFlow that does an add of these two matrices, call it matrix C's, and then we'll print it out. So let's actually go and do that. And again, it takes it a little bit, but here is the output from it. And sorry, I scrolled the screen there. And, here's my ones, which is just a 3x3 set of ones. Here's my values that I input as a constant. And you'll notice that when you add, you're adding this position to this position, so I'd expect a 2. And you're adding 1 over here to 3, so I'd expect a 4. So this is basically just adding two matrices together. And you can do this with vectors. You can do this with 500-dimensional matrices, provided they're the same size. So the size of the matrix makes a difference. And here's addition. There are things that you do with graphics that use things like addition. But multiplication is actually a more useful operation. If you do a matrix multiply, you can change the position, you can change the size of things that you are projecting in three-dimensional space. And every time that you see a polygon in a video game, that polygon has gone through matrix multiplies. So let's talk a little bit about how multiplication works. And if we have a matrix A and we want to multiply it by a matrix B to get a matrix C. I've got the formula down here for how it works, but there are some constraints. The first one is that A is, say, 2x3. That's what this m by n down here means. Would mean that B has to, and you notice we reused n right here. So that n has to be the same over here. So the inner numbers have to match. So you can multiply a 2x3 matrix by a 3x matrix. 3 by p in this case. And the resulting matrix that you get when you get done is the outer numbers, m by p, which is what you see over here is m by p. So there are constraints on the size of the matrix. You can't multiply arbitrary matrices together. But provided the size matches, you can do the multiply. Now I'm going to walk you through an example of multiplying. And there are lots of useful properties of when you want to multiply matrices. One of those is, I mentioned games and projections and three-dimensional space. They do lots and lots of matrix multiplies. In fact, graphic processors have hardware matrix multiplies built into them. So when I talk about this graphics processor having 4,000 cores, part of those is a single instruction that does a 3x3 matrix multiply so that it can do that in one step very quickly in a pipeline. Now, here is the little formula for doing a matrix multiply. Now, you apply this formula a whole bunch of times because the output is your resulting matrix C at position I, J. So basically, for every position that you'd have in the output matrix, okay, and that's m by n of them, you apply this little formula. And the formula says take the sum, that's what that big symbol means, from k starts out at 1 to n. So it has a loop in the formula itself, where it's going to go, if it's 2 by 3, then it's going to go through m, which is 2 of these things, okay? Actually, it's going to go through n of these things. It's the inner numbers that we're multiplying. Remember, the inner number has to match. And the n there matches with the n there. Sorry, I misspoke, but the n. And then we're going to take a sub I, which is this I as our destination, times b sub k sub j. That j is this j over here, the output location. So for every possible output location, we want to take and we want to do this sum across multiplying a and b. And k is the one that has to match in between. So before we go to the code in TensorFlow, let's actually go down here and take a look at a matrix multiply. And let's walk through a couple examples. Then we'll go back to the TensorFlow code. Now, I feel reasonably confident that you could sit down at this point and bang your head against some Python code for a couple hours and figure out how to do a matrix multiply. You could implement this. It would be annoying since we're talking about some sort of a function that you have to pass these matrices to that are lists of lists and index into them and all of these I, J, K indexes. And yeah, you could do it. It would take some effort. But let's at least walk through how it's done, and then we'll see how we do it in TensorFlow. So I have a matrix here. This is my A matrix with the A's in it, and it is 2 by 4. So the inner number here is 4. The inner number is 4 right there. And I have another matrix that's 4 by 3, so its first number is 4. So those first two numbers match. That is in our formula, the, if we go back to this formula, that's this k equals 1 to n. That's the n number is 4. So our inner loop, if we're working on this, is going to be 4. So we're going to go 1, 2, 3, 4, and we're going to go 1, 2, 3, 4 across the inner numbers. So when I'm calculating the outer one, this is I and j is 1 and 1. Then I want to take a sub 1, 1 times b sub 1, 1, a sub 1, 2 times b sub 2, 1. You notice those are switched in order. A sub 1, 3 times b sub 3, 1. A sub 1, 4 times b sub 4, 1. And then add up the results of all those multiplies and put it in my output location. So the input has a loop in it. The inner side has a loop in it that goes from 1 to that inner number, the 4. And then we do it for every location in our output matrix, which is going to be 2 by 3. So 2 down and 3 across. So we do it 6 times and run this thing on the inside. And when we do that, okay, I could walk through the same thing here with a different set of numbers, but basically you can see that we've got the 2's are constant and the second number changes, the first number changes, and the 2 is constant. So we do that for every one of these, all 6 of them, okay, and we end up with an output matrices. Now, you go, why would you do this? Well, it turns out that there's a way to take formulas, sets of them, turn them into a matrix. Trivial, because all we're going to save is the constant values. Solve the matrix to produce an inverse of a matrix. You can't solve every matrix because you can't solve every set of formulas. But you solve the matrix, and once you have that solution to the matrix, each new set of inputs that you want to run, all you have to do is just multiply. And you get your output result. So, provided that there is a solution to the matrix, you can do this and you can just very quickly go, okay, input, multiply, result. And since we build these graphics processors that are very, very good at multiplying matrices, this can be a fast thing, okay? And I think the graphics card that I have attached to this laptop, it has an external GPU, can do something around 600,000 matrix multiplies a second. Okay, of arbitrary size matrices. So not huge, but I mean this kind of size matrices. And that's a lot. That means you can solve a lot of equations very, very quickly. Certainly you can't do that inside the CPU of the computer, but with a graphics processing unit. And this is kind of the low end of a graphics processing unit. I have another computer that has 4 GPUs so that every single one of them is faster than the one attached to this. And you can build other systems that have way more than that, or go to faster computers and faster graphics processing unit and get millions of solutions per second. So this is downright useful. Now, you kind of need to know how this works to do something like take TensorFlow and multiply in a matrix. So in this case, I'm taking this matrix that's ones and I'm multiplying its elements by over here, and I'm getting an output result down here. So let's run multiply.